So good morning. Welcome to Krishna's classroom. I am Krishna Kumar. We begin with a new series of lectures today. This is entitled Analysis on RN. And this is the first talk in the series which gives an introduction to the topic and also work on the structure of RN where we intend to do the analysis or develop the ideas of analysis. So that's the scheme of things for today. Well, we are already familiar with analysis on R. Now R is a field. R is a one-dimensional vector space over R. R is a field with respect to the usual addition and multiplication. It's a one-dimensional vector space over R. And further, it has an order structure from which we can also define a concept of distance between two elements in R. So it is in fact a metric space. In a sophisticated language, it's a metric space. For every real number, you can attribute what you call a length, and then between two real numbers, you can define a distance using this length concept. So it is a normed linear space. So R is a normed linear space. Of dimension 1 on R. On R, here the associated field is R. Now we are interested to look at mappings from R to. And we had the concept of what is called continuity, differentiability, then smoothness, then we had the ultimate level of smoothness, namely analyticity. So all these things were there. So we had continuity, differentiability, smoothness, analyticity. All these concepts we already know. Then you see that we have analysis on C, and C is looked upon, considered as a one-dimensional vector space over C. Of course, you know that C is a field. So in the structure more or less runs parallel to this. Okay, and then we had again all these things explored, f from C to C. Then you had the concept of continuity, because we had the concept of what do you call a norm, which is the absolute value, and then a metric or distance function. So it's a normal linear space, therefore it's a metric space, therefore it is something like this, and whatever experience you had here could be explored on C, and with several pleasant surprises the analysis works out beautifully, with several pleasant surprises, notably the following. Very nice, if you have a differentiable function, complex valued function of a complex variable, then the real and imaginary parts satisfy certain conditions called the Cauchy-Riemann conditions, CR relations. And one more thing is that if a function is differentiable at a point, then the derivative of all orders exists, and the Taylor series expansion is convergent in some neighborhood of that point, and this is expressed by saying that f is analytic. So we have again continuity, differentiability, then you had analysis. You also had very nice study on what are called the singularities of the map and so on. So that gives you the theory of complex analysis. Very fascinating results are available from analytic functions. It's in some sense much more elegant and aesthetically beautiful compared with the real valued functions. For instance, for a real valued function, if you say it is n times continuously differentiable, then you cannot say anything about the n plus first derivative. Whereas if you have a complex valued function of a complex variable which is differentiable at a point, then all the derivatives of all orders exist, and a Taylor series expansion can be developed about that point, and the Taylor series converges. Okay. All these are nice properties that you have for complex function of complex variable. Now, one of the things that we would naturally like to do is, of course, in linear algebra, you have R over R is a vector space of dimension 1. C over C is a vector space of dimension 1. Both are fields. And then you have extended the notion of linear spaces to higher dimensional spaces, and we have the vector spaces Rn over which is an n-dimensional vector space. Now we shall make more detailed recapitulation of these ideas soon, before we embark on functions defined from Rn to Rn. That will be our ultimate objective, to study functions defined from Rn to Rn and how one can naturally extend the concept of differentiation, derivation. And then, we are not making any assumption on the functions. How functions can be studied through their linear approximations. So this is one of the things that we will explore. In this context, the derivative of the function becomes very important. So we will have to completely reinvent. There are some inherent problems when you go from functions from R to R to say functions from Rn to Rn. Okay, and these problems have to be addressed, which would require, when we work on differentiability or derivative, we would have to reinvent the concept of derivative altogether on R, and then in a form in which you can extend it to the general context, namely from functions from Rn to Rn. And that is one of the things that we would like. Okay. So a natural generalization is sought after here. And then of course we are generally dealing with vector valued functions of a vector variable, which means functions of several variables. And we are already familiar with the concept of partial derivatives, or even going to further, we are familiar with what is called directional derivatives. And we will have to connect them with what is called the derivative, if at all it exists at a particular point for such functions. That is something that we will have to explore. Okay? So all the conventionally known things will have to be connected with the new ideas that will come out from it. Now this is one of the tasks. Second task, as I was telling, that in mathematics, when you deal with the linear functions, there's a rich linear structure that is available, or from which lot of things come out. When you go to nonlinear functions, obviously you run into deep waters. And this is a place, what we normally do is, as we do in mathematics or in any science, we try to reduce the whole thing into the premises. So locally, you try to replace the given function by a linear approximation, the best possible linear approximation, and then study the properties of the corresponding linear map. And because the two stay close together, as I said, it's a close approximation, it's the best possible approximation that we look at. So we hope that the properties of the linear map will give you enough insight into the properties of the nonlinear. So this is one of the approaches that we normally take. That is generally what you call a nonlinear problem is linearized and studied. And wherever the linearization is a nice approximation to the nonlinear problem, a lot of information can be fished out from the study of the linear approximation. Now this is one of the reasons that we study this. A second point is that so there's enough reason to develop everything to functions from Rn to Rn, generally vector valued functions of many variables. Okay. What about what more? You see that quite often while dealing with many physical problems, one would not be working on what are called spaces like R. Okay, quite often, as you see, we may not be interested in studying, things in R3. Instead, we may be interested in studying a problem on some surface, like say sphere or a cylinder. Okay, and in that case, what kind of calculus that you can use, or what kind of analysis you can use? So certainly you are encountering a sort of curved surfaces. Okay. In general, the curvature is not equal to 0 like a plane. If it's a plane, it's quite simple. Again, you are in a familiar ground. But the moment there is a curvature, then you have problem. So you have to develop analysis on curved surfaces. Many problems demand that. And because of that, what we try to do is we want to develop analysis on curved surfaces. So what kind of surfaces? So locally what you do, if you have a well-defined surface, say in Rn plus 1, that is an n plus 1 dimension, it becomes an n surface, like what you have a sphere in R3, okay, or a hyperboloid in R3, or an ellipsoid in R3. These are all locally two-dimensional, in the sense that at every point on this surface you have a tangent space which is a plane. Okay, so it's a two-dimensional tangent space that you have. So if you can develop analysis on these kind of tangent spaces, from that you can go to developing analysis on the curved surfaces. Now this is what is called doing analysis on manifolds. So that is our final objective, is developing a rough definition of this would be what you call a locally Euclidean space, in the sense that a tangent space in that, or it has got a close approximation by, say, locally. So locally Euclidean spaces. Now this is called locally Euclidean. So for that, the preliminary task would be developing analysis on Rn, generally mappings from Rn to Rn. So that is the brief introduction I want to give you. So our objective will be to pursue this task, to define, to study functions from Rn to Rn. This will be our task. Okay. So before we talk about functions from Rn to Rn, I think it is worthwhile to spend some time on the structure of Rn. So work with structure of Rn. The model for Rn, where you have a lot of insight into, is the real line, which is probably trivial, and then R2, that is the usual two-dimensional plane that we are familiar with, and then to the space we live in, namely R3. Okay? So we try to look at everything in these spaces to get a feeling for things. Then we look at the generalizations into a more general space like R. So that's what we are. So we start with the definition of R. Rn we define as a set of all n tuple except with xi belonging to R for I equal to 1. So essentially this is R cross R n times. So with this notation, R1 is now on this set we introduce two operations what are called vector space operations, namely addition and scalar multiplication. So we see that suppose x this denotes the element x1 then we define x plus y, that is the sum of x with y, is defined as and then the scalar multiplication for C belonging to R, we define scalar multiplication by Cx equal to now you observe that For x belonging to Rn, y belonging to Rn, x plus y is an element of Rn. So also for the scalar C, the scalar multiplication gives a vector in this corresponds to the usual vector space operations in R2 or R3 or even R. Okay, so that we are familiar with. And of course, I want to make a remark there. So you take the case n equal to 2. Then what you have is the following. You represent the plane by a look at the plane and then introduce a coordinate system given by 2 copies of R tied together at the 0 point and keep it orthogonally also, it doesn't matter. So we without we don't want to confuse at this stage, we'll keep it orthogonally. So usual Cartesian coordinate system that we introduce. Now you see that since already some unit length is marked on these 2 lines, what are called the axes, we have now every point in R2 has a, we designate this by x, then this is x1 and this is x2. So this point is considered as a vector which is acting at the point 0, 0. Okay. Now we choose another point. So every point in R2 is identified by a vector. And go to the details of vectors. That appear in nature, and it is from physics these ideas emerge. Because in physical sciences, certain objects to study the nature were identified as vectors like displacement, velocity, acceleration, force, etc. Now, they were geometrically identified with a line segment acting at a point with its length proportional to the magnitude of the vector and the direction being the direction in which the vector acts, namely like force acts or the velocity acts and so on. These are the familiar concepts from physics, so I am not going into the details of that. Then of course experimentally it was asked, how do the vectors act? Now this came from the problem. Suppose there's a object moving in a plane. We are now dealing with in a plane, and there are 2 velocities acting over it. Okay. For example, you think of a boat moving in a in a river, obviously there is a velocity imparted on it by the flow of water. There is the other induced velocity that comes from you are driving it. Drive it with a certain velocity. Now these two may not be in the same direction, because if you are crossing the river, then you will have to go across. So you will be driving it in such a way that you reach from this point of the bank to the opposite side of the bank. So you have now, see, something like this. You have to go from A to B. There is already the river flowing in this direction. Then you have to go from here to here. Now there is the problem. Which way you give a velocity to your boat so that it reaches here? It emerged out of experience that you will have to row the boat in the upstream direction, some direction like this. Okay? So that this plus whatever be the velocity that you have here will together add up to a velocity here, okay, in the desired direction. This is the direction that we want to. Therefore, the question is, how do you fix the velocity on the boat so that you are always moving from A to B? This is the direction in which you are moving. And initially, the experience showed that you will have to row upstream. So usually you row upstream and then you finally reach here. Or maybe a bit path you go, because you cannot really keep it like this exactly. But anyway, you found that if you start rowing it in the direction in which you want to go, then suddenly the boat will reach elsewhere. Okay? So to adjust to that, you will have to row towards upstream. That's the experience. Therefore, a systematic study of this problem was made, and it ended up in asking the question, how do the vectors add? Okay? Some nice experiments were devised, and then using that, it was resolved that vectors add using parallelogram law. It is the parallelogram law of addition that works there in the vector addition. So it is found that if you have a vector acting here, another vector acting here, so suppose this is u, this is v, then what you do is you complete the parallelogram with these vectors as the sides and then draw the diagonal, and this diagonal will give you what is called u plus v. This is nothing to do with mathematics, it has to do with physics. It's a physical experiment from which this information was attained, and again it was postulated that vectors add using parallelogram law. It was verified. Okay. So as I said, it is physics. I mean, I cannot say that it is proved that they add using parallelogram law, but it was verified in several situations, and therefore it was postulated that vectors add using parallelogram law of addition. So that was purely a physical fact. And then, of course, to understand this, so this was the mathematical modeling, or what you call the geometric modeling of the vector addition. That is, the vector has a point where it acts, a direction in which it acts, and a magnitude. Okay, so these two vectors U and V are different. Even if they have the same magnitude, they are different because they act in different directions. Okay, even if two vectors act in the same direction, their magnitudes are different, then they are different vectors. Okay, and then of course the sum can be formed. Later on, this was not a very easy way to understand what you call the resultant of the two vectors. Then of course, information already available from Euclidean geometry was made use of. The first step was identifying a vector with a point in the Euclidean plane, and it was identified with a pair of numbers x1, x2 in some order. Okay. So every point in the plane is now identified as a vector. The direction of the vector is the line joining 0, 0 to the point x1, x2. The point where the vector acts is at 0, 0. This is 0, 0, the origin. And then the magnitude of the vector is essentially the length of this vector. That's the number. Okay. So this is the information that is available. Now it was asked, suppose you have two vectors, say one x and the other one y, then you know what it is, the sum of these two vectors, x plus y is, this is the resultant vector. So you know the coordinates of the point, the coordinates designating the vector x, the coordinates designating the vector y, say x1, x2 and y1, y2 respectively. And then your question is this, you know what x plus y is geometrically, but what are the coordinates of x plus y? It is very easily proved that x plus y has coordinates and that is amazing and beautiful, because you see that now once you identify the vectors with a coordinates with respect to a certain coordinate system, then you are easily able to add two vectors. And all that you need is add the corresponding coordinates of the two vectors to create a new vector. So the sum was defined like this. In the same way, if you have a vector, then multiply by a scalar, that is actually scaling it up. Okay? So you have a vector, then something like this, you have a vector in the same direction with, say, obtained by scaling it by a scalar c. Okay? That means the length of the vector, the direction of the vector is the same, the point where it acts is the same, but the length of the vector is now c times the vector. And then of course you ask what are the coordinates of that scaled version. So you can easily see using calculus, you can easily see that this is cx1, this height is cx2. So that is that. So it is actually multiplying every coordinate by the corresponding scalar. Now this was also mathematically obtained. Therefore, you have now two operations possible. One is this you call Cx. This is x plus 1. Now it is quite simple to work with vectors in space R3. Okay. Once again, using geometry, one could to solve all these problems and found that once the vectors are represented in a coordinate system, then the addition of vectors is represented by adding the corresponding coordinates, the respective coordinates, and scalar multiplication amounts to multiplying the respective coordinates by the scalar. Now this was quite simple to get in the case of R3. So this idea extends to R3. So from R2 to R3. R3 also you have and Cx. All this comes from physics. It's not a mathematics. So we have defined or we have designed the mathematics required to handle the physical reality. Okay. So this is no. Now you see, obviously you come across or situations where you have vectors with n components or even infinite components. Okay, in that case, how would you define addition? So that is a generalization that you see. First level of generalization is go to Rn, where Rn is defined as the ordered n tuple, and then you have sum of two vectors x and y defined as the vector obtained by adding the respective components, and so also the scalar multiplication. So two operations like addition and scalar multiplication, and when you add two vectors in Rn, you get a vector in Rn. So essentially, addition is a map from Rn cross Rn to R. And multiplication is from R cross Rn to R. So these are the two operations that you have. This is x comma y map to x plus y, and c comma x map to c multiplication. So this is addition and scalar multiplication. So these are two maps from Rn cross Rn to Rn, R cross Rn to. Now naturally you ask, what are the properties of this map? Okay. So you first thing that you observe is, I am not going to do the details of this, but you realize that the addition is a binary operation and for C belonging to R and X belonging to R, and Cx is a vector in R. So these properties are there. Now what do we have? Observe that, see, addition is an associative operation, which means, see that x plus y plus z equal to x plus y plus, this you can easily verify, and you will have to use the corresponding properties of addition in R. Then you have x plus y equal to y plus x. That means addition is a commutative operation. It's associative, commutative. Then you have, there is a vector called the zero vector with the property that x plus 0 equal to 0 plus x, which is equal to x. This is a zero vector which corresponds to the point 0, 0, 0, etc. at the origin. So 0 corresponds to the n tuple with each entry equal to 0. Then you have, for each vector x, there exists a vector minus x such that x plus minus x equal to 0. Okay? So this is what is called the identity element. This is called the inverse element. So for every vector there is a unique inverse. There is an identity element in the space, and therefore you see that Rn is a abelian. Now that is purely what happens when you add vectors with respect to addition. Now when the second operation comes into the picture, what happens? Okay. See that C x plus y, Cx plus C, that is the distributive. Then you have 1 into x is equal to x itself. Then this is 1 is the unit element in R. Then you have the additive identity element 0. X will give you 0. Now this is the 0 in, this belongs to R, whereas this belongs to R. Okay. Then you have got C plus D of x equal to Cx plus Dx. Then you also have C dx. This is equal to C for C and D belonging to R. So you have said what happens when you take the identity element, multiplicative identity element in R, additive identity element in R, and then multiply what you get. You know what you explain it. So if all these properties are satisfied, then you call it a vector space. And in fact, you can have the generalizations, but we are only interested in R and company. So we are not going into the details, but those who are interested can go to the study of vector spaces. Okay, right. So let me so Rn over R is a vector space, and the whole model is R2 or R3, where you test things, the ideas that we make to understand what's going on clearly. Because you can geometrically conceive those spaces easily and then work on them. And then, analytically or using analysis, you can, or abstractly, you can extend it to R. This is the whole idea. Now, what are the other structures that come? So, let us explore this. You see that if you take R3, this is R cross R cross R, your usual XYZ coordinate system that we use. So, this is 0, X coordinate, Y coordinate, Z coordinate. Now, you see that you just do not have to know all the vectors in R3 to understand it. Okay? In fact, you can get representations of this. So, what do you do? Suppose you take a non-zero vector, x not equal to 0, and you take Cx, or what you call C1 Cx, where C belongs to. Now, as you vary C over R, you generate the entire line along the vector x. Set x is a non-zero vector. Therefore, there is a unique line along which the vector x lies. So, it covers a certain part of your R3. Now, what do you do? Suppose you choose another vector y along the same line and then apply the addition and scalar multiplication. Do you get anything new? Nothing. You keep generating this line and nothing else. But you see that suppose I were to choose a vector y which is not along this line. Okay? Then, so let me denote this line by the square x. That is the line generated by x. If y does not belong to this and you apply the same technique, what you get will be, you will be generating another line, which if you want, you designate by y. In the same way you can designate y. Bracket. Now you see that you use this. See, as I said, this is if you take cy, you get only lines or points on this line. But suppose you use c1x1, c1x plus c2y, or let me use tx plus sy, t comma s belonging to. Then what do you get? Look at this whole set. That is, let me just denote by x comma y. Bracket. Designate by t comma comma S belonging to. What is this set? This set, you see that it is the plane generated by these two vectors. Okay. It's a plane generated by these two vectors. Right? What have I done? I have chosen y not along the vector x. Y is not equal to 0. And then I have looked at the linear, what you call Tx plus Sy for x and y belonging to the fixed x and y that we have chosen. And then T and S allowed to vary over the whole of R. What do I get? I get a set of points in space. But you see that you can easily show that this covers a plane. Okay? Right? And you can easily work it out. So find out this. So exercise. Determine the equation of the line. Determined by the vector x3 x not equal to 0. Now this is one problem. The second problem is given x comma y belonging to R3, x equal to x and y are not along the same line. Now this I take not equal to 0, this I take not equal to 0, by which I mean one of the components is at least one of the components is different from 0. And I also assume x and y are not along the same line, which means there does not exist, that is there does not exist a scalar C such that Cx equal to y. That's a condition. Then find the equation of the plane by these vectors. Okay, that means essentially still you see that if you do it, you see that it doesn't cover the whole of R1. There is a lot of space which is not covered by this one. Now you run the exercise again. What do? You have a non-zero vector which is not lying in the plane determined by x and y. Okay? So choose a z which does not belong to x, y. Now consider is defined by Tx plus Tsy plus Rz. Okay, and T comma S comma R which means every point in R3 can be written as a vector of this type Tx plus Sy plus Rz, where T, S, R are specifically chosen from the knowledge of the vector that you have. So given U, and this T1, S1, R1 are uniquely determined. So every element of this collection is in R3, and any vector in R3 can be expressed in this form. Okay, so this is clear. So X, Y, by definition is contained in it. If you prove this, so this implies so you see that essentially you need the knowledge of these three vectors X, Y and Z. Okay? This is not the this set that I am speaking. This is the one coordinate, two coordinate, and three coordinate. So you can choose three vectors carefully, and using that you can construct the whole of R3 through what is called scalar multiplication of these vectors by appropriate scalars and then adding. That means the two operations that are already available in your space. Okay? So you don't need information of more than three vectors to create or to construct or to craft the whole of R3. All that you need is three vectors, carefully chosen. Okay? So let us make these ideas more clear through some definitions. We define what is called a linear boundary. Suppose x1, xk are k vectors then the vector e1 x1 plus e2 x2 ekxk is called for e1 is called a linear combination of x1 right, and if you take this one, if you define this class, because you know that you get a vector, so you get a vector, this is a vector, this is a vector, each one is a vector, and the sum of these vectors is again a vector. So you get a vector in Rn. So if you denote by xk within square bracket as the set of all p1 x1 xk for pi belonging to R for I equal to 1 k. Then xk is called the span of this is what you call the span of the vectors x1, x2, etc. xk. Now what one can prove is that span of a set of vectors x is contained in R3 when that is x equal to k is a vector space with the same operations, same rules of addition, and scalar multiplication. This you verify. I mean, that's quite easy to verify. What you want to, you take a vector from x, take another vector from x, show that the sum is again in x. So what you have to do is the following. If you y1, if x belongs to x and y belongs to then for c belonging to R, cx belongs to verify these properties. Okay, then you can show that this contains the zero element. For each x you have the corresponding minus x in it, and then all the properties that are required for a set to be a vector space will be satisfied. So it's a vector space in itself. So X is a vector space. Okay. The span of any set of vectors in Rn is a vector space. The span of any set of Rn is a vector space. And you see that you call this, so span is generally a subset of Rn. It is also a vector space in its own right, therefore you call it a subspace. Okay? I will say that. And you say that this particular vector space, this subspace is spanned by, we say that this subspace is spanned by vectors we have chosen to consider. Through linear problems. So that is the idea. I think I will stop here and possibly continue with it in my next lecture. That means I will introduce ideas like what is called linear linear independence, and then the concept of a basis, etc., etc. So this I will do next time. Okay, so thank you very much.